Hello, I'm Yongjin Cho of Rehabilitation Biomechatronics Lab. Today I present the final result of soft exosuit system for ankle assistance. Sohyun Moon and I will do the project together. In this presentation, I review the background of our project. Then I'll talk about the key tasks and how it was evaluated. Then I'll check whether we have achieved our goals. Also, I'll talk about the limitations and future works of our project. As the percentage of old people increases, the number of neurological disorder patients are also increased. The typical symptom of these people is gait disorder. So, to assist patients with lower limbs, exoskeletons are normally used. However, as these robots are made of rigid frame like metal, its weight is heavy and the size becomes bulky. Also, as the motor is placed near the joint, if the joint misalignment happens, patient can be damaged severely. Therefore, to assist patients walking more naturally and safely, we developed the soft exosuit system, which is made of soft textile material. To evaluate the soft exosuit system for ankle assistance, we should accomplish two steps of procedure. First, we should develop the soft exosuit platform. The platform consists of textile suit and actuation unit. The detailed tasks are actuation unit development and ankle power transmission mechanism development. Also, the textile suit for ankle and calf should be weared. After the development of platform, we should control this robotic system. To assist the ankle, we first have to know the characteristics of gait. To do that, we use IMU sensor. After that, we implement the position control based on gait detection data. The tasks in the blue box will be done by myself, and those in the red box will be done by Sohyun Moon, my colleague. About the progress report, we thought we should present everything about our project, so we present the task about other persons one. Sorry about the misunderstanding. Today, I will present what I've done for the project. Before the main contents, I think you're not familiar with this kinds of research such as human body. So I explain the essential concept to understand my presentation. That is dorsiflexion and plantarflexion. When the ankle is stretched, it means plantarflexion motion. On the other hand, when the ankle is flexed, that is called dorsiflexion motion. In this presentation, I will sometimes call plantarflexion as PF and dorsiflexion as DF. First, the actuation unit should be developed. The primary part of actuation unit is motor module. The motor module is consisted of shaft connector, pulley, and motor. Pulley is connected with cable and wind up when the motor is rotated. Shaft connector is the only part which is practically combined with motor. As the shaft connector is connected with motor and pulley together, it can transfer the power of motor to pulley. The parts have several holes to reduce moment of inertia. Also, by deploying the bearing, we can eliminate vertical load from gravitational force. And the motor can be activated upon the motor holder module. This is the total platform we developed. The system is placed on 3-floor rack. At second floor, two power supplies are placed for providing power to both motors, and load cell power supplies and amplifiers are also placed. At the top floor, SVC, DAQ, motor drivers, two motor modules are placed. Motor module is consisted of a motor, a gearbox, encoder, and pulley module. At the motor module, the Bowden cable is also connected. The inner cable is connected with pulley, so when the motor rotates, cable can transport the force to ankle. The textile suit is made of soft textile material. It is composed of waist belt and cuff wrap. This is Sohyun's part, so I'll briefly explain about this. We can find out the angle of ankle using gyrometer of IMU. Using this, we can find out whether the ankle is on plantar flexion motion or dorsiflexion motion. Also, with IMU sensor, we can measure the angular acceleration and velocity. Using the timing when the direction of velocity and accelerations are changed, we can determine the timing of stance phase and swing phase, which is represented by circles and stars. Therefore, we can find out the total gait cycle time. To make motor trajectory for ankle assistance, we need to model the system. Although the force is transmitted through the cable, the body and suit are also changed. Therefore, we need to model the system of the body, cable, and the suit. When the force is generated by motor, two forces are applied at the system. One is cable itself, the other one is from the suit. Also, the system has several sources of compliance. Figure at the right shows those sources. In the Bowden cable, outer shaft can compress, inner cable can stretch. Textile material of suit can stretch too. The body itself can stretch because of tissue between the textile suit and bones. So they have stiffness about body and cable and suit. The relationship between force and displacement can be represented by total stiffness, which comes from three kinds of stiffness. The equation for total stiffness can be shown at the slide. Then we need to determine the force of assistance. Although over 500 Newton of average power is needed to lift up the body at the propulsion phase, our maximum force is 250 Newton because of hardware limitation. The maximum force of our dorsiflexion is 150 Newton, which is less than plantar flexion force. However, the magnitude is enough because it has to bear not the whole body but only ankle. Even though the neurological disorder patients have symptoms of high stiffness when they do dorsiflexion motion, the 150 Newton of maximum force is enough. As we know the desired force and stiffness, the length of displacement can be calculated. Based on the displacement, the rotation angle of motor can be determined too. Using the data from gait detection algorithms such as stance phase timing and total gait cycle time, we can make our assistance trajectories. The timing of start and end of motor rotation is based upon desired displacement of cable. The shape of velocity trajectory is trapezoidal shape. Using the equation of trapezoidal trajectory, we can develop the dorsiflexion and plantar flexion motor angle trajectory. Using these trajectories, we should control our platform. Upon the desired trajectory, the control schematic diagram of soft exhaust system can be shown at this figure. Using the desired trajectories, we can make our desired velocity. Also with velocity controller, we can make proper assistance forces. Our final object is a real-time gait detection and modification of trajectories. However, as we are forbidden to test to human, the mergence of real-time gait detection and trajectory planning is not possible. So in this project, we first begin with the control with fixed desired trajectories. And when the force is transported, the tensile force is applied to cable, and the torque caused by this force acts in opposite way of our desired trajectory. So to eliminate this term, we can calculate the magnitude of this torque by using the data of load cell sensor. So we will run the experiment with and without the feed-forward system. When we do the experiment, 30 gauge cycle is measured per one test. This is the result of our experiment. First, we compare the range of motion of ankle with that of healthy people. In case of plantar flexion, the normal value is 26 degrees. Without feet forward, the range of motion is decreased 4 degrees. However, only 1 degree of value is changed when we consider disturbance. In case of dorsiflexion, the aspect is similar. When we do feed-forward control together, it can reach to help people's range of motion more. The mean root-mean square error about the motor angle is also decreased when we used feed-forward control, and the deviation is also decreased. Now I'll review our goals of the project. We can develop the soft exosuit assistance platform. We evaluated the actuation unit and power transmission system using board and cable. Also, the textile suit for ankle was also made. The characteristics of gait was detected by gait detection algorithm using IMU sensors. And position control was also evaluated. However, that was not a real-time assistance. Because we cannot test to human, the experiment was about the fixed trajectories. There are some limitations of our projects. As I said before, because of experimental limits, we cannot evaluate real-time gait detection and trajectory planning. So after we get the permission to test human, we can show the full real-time gait assistance. About the control system, although we almost get to the value of healthy people, there are some errors still exist. To reduce the error, the control scheme must be improved. Also, we primarily consider the accuracy of control system in this project. However, we need to consider the safety of wearer too. So in future work, we need to update our control scheme to ensure the safety of our patients by controlling the timing of assistance. Now I will summarize our project. The need of gait assistance for neurological disorder patients will increase. The soft exosuit system we developed is a good solution to alternate current exoskeleton. Using the position and velocity control with feed-forward control system, we can increase the accuracy of our system. So in future work, we need to consider the stability and safety of system too. This is the end of the presentation. Thank you for listening.